Hello, everybody, and welcome to the Northwest Quantum Nexus seminar series. My name is Nathan Baker, and it's my pleasure to welcome you all and to cover a few housekeeping items prior to turning it over to Professor Kai-Mei Fu for the formal introduction. The Northwest Quantum Nexus seminar series is part of the Northwest Quantum Nexus, and you can find more information about that at the website listed at the bottom left of the slide. Including information about how to get involved in some of our upcoming activities, including additional seminar speakers. So before I hand it over to Kai-Mei, I wanted to start with a disclaimer and a code of conduct. This seminar is being recorded, and by attending this meeting, you may appear as an attendee in the recording. So your questions and comments in the question and answer box will also be part of the recording. And NQN is dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards, and we encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance to or remove any person from an event at any time at its discretion. So with that out of the way, I'll turn it over to Kai-Mei to introduce our speaker today.
Thank you, Nathan. So it is a great honor of mine today to introduce today's NQN seminar speaker, Robert Raussendorf. Robert is a physicist and quantum information scientist. He is the co-inventor of a very powerful paradigm of quantum computing, the one-way quantum computer, which is also known as measurement-based quantum computation. He works on the foundations of quantum computation and error correction. He received his PhD from Ludwig Maximilian University in Munich in 2003 and is currently a professor at the University of British Columbia. Before we start, I want to strongly encourage, at the request of Dr. Raussendorf, that if you have questions, to please put the questions in the Q&A in real time so we can address, so he can address any questions you might have during the talk. So with no further ado, I'm going to hand the presentation over to Dr. Raussendorf.
Hello, I hope you can hear me. I'm still struggling a little bit with the system. I should. I have the control bar and I need to. I hope it was giving me options to share. I wanted to share my slides. Okay.
Do you see the little up arrow?
Yes, I clicked it, and now I have Windows. Doesn't give me too many choices.
There's two windows, and then I think there's like another prompt underneath it that allows you to click on it to also just share particular.
So what happened now? I have all the controls have disappeared. You probably see my, you see my entire screen. Oh, no. Okay, let's see. Okay, let's try to, let's see. I've clicked it again. Okay, let's see. Are you sure you want to share? Yes, I want to share. Okay. Now what are my options? Yes. Good. Okay. Problem out of the way. So it seems you can see my slides. Is this the case?
Yes, we see it in a PDF viewer right now.
Yes. Okay, I think this is the best we can do here on my Mac. Final check. You see my cursor wiggling across the slide?
Yes.
Okay, good then. I think we're good to go. So let's get started. So welcome everybody also from my side. This talk is called a computational phase of quantum matter. So let's see what that is. This is work done with Dong-Sheng Wang, David Stephen, Cihan Okay, and Hendrik Poulsen Nautrup. So these people all passed through my group, but they're in all sorts of places now. Dong-Sheng is somewhere in China. David Stephen, I think, is returning from the Max Planck Institute of Quantum Optics in Garching, Germany, to the US, to Boulder, Colorado, if I'm not mistaken. Cihan Okay is in Ankara now, and Hendrik Poulsen Nautrup is in Innsbruck, Austria. Okay, good. So now let's see what this is, computational phases of quantum matter. So to some of you, the question we'll be looking at might look a little bit like play, but there is a serious question behind it. And let me begin there. So a question that you may very reasonably ask is the following. If quantum algorithm development would be stopped today and all energy in the field went into implementing the existing ideas that we've already had, would that suffice to lead quantum computation to success? I guess that's a very reasonable question. I believe many of you have asked that question yourselves. My personal answer to this question is no, and that kind of guides my research. So what I do is I look at the foundations of quantum mechanics and just kind of browse through certain material and wonder what of that can I use for the design of quantum algorithms. What can help with quantum algorithms with what we know about quantum mechanics already? Okay, good. And also my talk that I'm going today is informed by this question. So let's get started. Liquid phase of water, not very quantum, but it leads us kind of into this talk. So what you see here is a stylized phase diagram of water, or at least of the liquid phase of water. So the horizontal axis is temperature, vertical axis is pressure. And so the point is that everywhere in this phase diagram of water, in this liquid phase of water, pretty much everywhere you find life. You have ourselves, animals, humans, at intermediate temperatures and low pressures, but life is elsewhere. You have it at cold temperatures and outrageously high pressures. You have it at only cold temperatures and low pressures, but you also have it at high pressures and very high temperature, I mean, boiling. Yeah, life is everywhere in this phase, and we are looking at something like this. So we are looking at a phase of matter. We are looking at a complex property like life is. I mean, life is not something like viscosity or density or something like that. It is complex, and we are looking something like this, but still different. So our phases live at 0 temperature. They are phases of spins. So we are looking at spin lattices in 2 dimensions and in the presence of symmetry. So these are our ingredients. This is our domain. Yeah. And so then we have quantum mechanical phases, ground states of certain Hamiltonians. And that is our object of study. And we look at a different complex property, and that is computational power. So what we find is that states that live in these phases, they can have computational power. And that is what the talk is about. Okay, so here's the starting point, just kind of to introduce a little bit of technique. It was already mentioned in the introduction. Thank you. Measurement-based quantum computation. So the way measurement-based quantum computation comes in here is by how the power of quantum states, the computational power of quantum states is utilized. So namely, we measure them and thereby compute. The first example of this phenomenon was discovered for what's called the cluster state. So the 2-dimensional cluster state is a computationally universal material. You can implement any quantum computation on it simply by measuring the particles in that state. Today, we're going beyond that. So we show that the same holds not only for particular quantum states like the 2D cluster state, but it holds for entire phases of matter. That is, you can be anywhere in a certain phase of matter and you have the same computational power. So that's what we want to talk about today. All right, so now to the fine print, let's just kind of recap what I already said. So we consider phases of unique ground states of spin Hamiltonians at 0 temperature. In the presence of symmetry, we will impose suitable symmetries, you'll see later, and for lattices in spatial dimension 2. Okay, so spatial dimension 2, symmetry, zero temperature, ground states. That is our setting. And for that setting, we show the following. Oh, by the way, I have lost the Q&A. So if there is a question, maybe somebody could just kind of stop me and say there's a question and read the question to me so that I can answer it. I, again, would like to say that I encourage questions throughout. But I can't see any right now. So please, whoever has a kind of the ability to inform me about questions that are being asked in the Q&A, please let me know. Okay, so what is it that we show? We show that for the setting that I just mentioned, now there exists at least one quantum phase of matter which is universal for quantum computation. So anything that you can do in the circuit model of quantum computation, you can do with the help of measurement-based quantum computation for these states in a suitable phase of matter. And so the point is, it doesn't matter which state you pick, the computational power is always the same. The computational power is uniform across the phase. Good. So that is what the talk is about. Okay, here's an outline. So there is a background. There's two basic concepts to review. The first is symmetry protected topological order, and the second is measurement-based quantum computation. Then we have maybe another background section, but this is now very close on this subject, computational phases of quantum matter. And I'd like to tell you what our motivation is, our technical motivation, why we are looking at this problem. I have given you our overall motivation with my very first slide, but now we want to get a little more technical. And I will restate the motivation in more technical terms. And I will also give you a short history of the question. So this started with a paper by my colleague Akimasa Miyake, who was then at the Perimeter Institute in Waterloo, and who is now in Albuquerque. Yeah, that was in 2010. Okay, and from there, I want to review the history of the subject for you. And then finally, I come to the central topic of the talk, which is a computationally universal phase of matter. And you need to go to two-dimensional systems to show this. The history is focused on the simpler and better understood one-dimensional case. Okay, so I think it's time to get going. Part one, background. First concept to discuss here is symmetry protected topological order. And it's just the standard condensed matter physics notion of SPT, so nothing new for condensed matter physicists here. So what is shown here in this little plot is a phase diagram. So we have a Hamiltonian, we have its unique ground state, and the Hamiltonian can depend on parameters. So this is what's giving us the phase diagram. And so what we want to know is when are two ground states at certain points here in the phase diagram, when are they in the same phase? And here is the condition. So for them to be in the same phase, we need to have a path connecting them. So there's a path of ground state, continuous path of ground states, connecting them such that nowhere in this path, nowhere on this path, the energy gap above the ground state closes. There's always a finite gap above the ground state all along the path. When we can find such a path, then the endpoints are in the same phase. So that is the condition for any zero temperature phase, but now in addition, this is symmetry protected. So the phase space here, or the parameter space, is restricted. We require that our Hamiltonian is invariant under the given symmetry everywhere. Yeah, so that is how we restrict our search space. Our space is restricted to symmetry respecting Hamiltonians. Okay, that is our our setting. So this space decomposes into various phases, and those phases are separated by points where the gap shrinks to 0. Good, that is SBT. Measurement-based quantum computation. I have 2 slides on the subject. One is just a slide of preparation. So just kind of let us step back a little bit and just recall that there is 2 fundamental ways of evolving quantum systems in time. One is unitary evolution. This is what happens in the Schrödinger equation. And then there is projective measurement, which is what the Born rule describes and what the Dirac projection postulate describes. These operations are very different. Unitary evolution is deterministic and reversible. So if I know what my initial quantum state is and what my unitary transformation is, when I apply this unitary, I know exactly what state I get. So that's the deterministic part. And also I can undo the unitary. And so this evolution is reversible. Projective measurement is the exact opposite of that in every respect, pretty much, you can think of. So first, it's probabilistic. So say we measure a spin, z component of spin. The outcome that we get according to the rules of quantum mechanics that we know is probabilistic, not deterministic. It's someone's rolling dice. And also it's irreversible. So after the measurement has been performed, the state changes and it is impossible to go back to the state before measurement. So measurement really changes the measured state. Okay, so just kind of this as background. And with this, we move on to measurement-based quantum computation, because if you use unitary transformations to make your quantum computer, that leads you to the circuit model. If you use measurements, it leads you to measurement-based computation. Okay, so now, what is it? I mean, there's really a lot to say on this slide. I must cut it short. So, but what we have here is a 2-dimensional grid of qubits. So every symbol, arrow or dot is a qubit, and these qubits have been prepared in a particular entangled state. Could be a cluster state, could be something else. But now the computation proceeds by measuring each particle on that state. That is how the computation is driven. So information is written onto that state, processed on it, and then read out from it again by those local measurements only. So no unitary evolution ever takes place in this computation. And maybe with a bit of imagination, you see a circuit coming up here. Yes, you can think of this as a circuit simulator, but we don't have the time to go into all of that detail. Just maybe one more point is to say that universal resources exist. So you can have quantum states for which this scheme of quantum computation becomes universal. Cluster state is one example, the AKLT state is another. And what we will talk about today is entire phases of states. Good, so that was the background part. And I move on to the second part of my talk, which is a short history of this notion of computational phases of quantum matter. Let me begin with my motivation. It says here motivation number 1, because there could be many, but I only give you one motivation today, and that is the interplay between measurement-based quantum computation and symmetry. So by the way, the picture that is on this slide, I will not explain now, I will explain it later. But I will go through the questions here. So the question that we ask is, can schemes of measurement-based quantum computation be classified by symmetry in a similar way as elementary particles can? I mean, we remember that from everybody here, I suppose, remembers that from their university courses in particle physics or even condensed matter physics. So symmetry is a very powerful classification scheme in physics. I mean, it helped organize the particle zoo, helped organize other things. And so the question is, does it also help us understand quantum computation better? And the first question we can ask is classification questions. So there's various schemes of measurement-based quantum computation around, can they be classified by symmetry? Yeah, that's the first question. And if that is successful, we can ask a further question, namely, how does this help us understand quantum algorithms? Okay, so this is the hope is that we learn something about the green question with this whole approach, but that is certainly in the distance. Okay, anyway, this is the motivation. Now let's talk about the history part. So it begins with this paper by Akimasa Miyake that I already mentioned from 2010. Yeah, so what did Miyake do? So he looked at a hybrid scheme, half measurement-based, half adiabatic, of quantum computation. So the measurement-based part was that essentially this computation was driven by measuring particles. The adiabatic part was that the state here that was considered was the ground state of a Hamiltonian, and before particles could be measured, they would need to be adiabatically decoupled from the remainder of the chain. And about this scheme of computation, Miyake observed that you didn't need to know the precise details of the state that you were computing with. It sufficed to know that a certain symmetry was in place. Yeah? So that was the insight, and he immediately realized that this phenomenon is related to symmetry-protected topological order. So that was the beginning of this direction of research. Okay. Next paper on the subject that I want to review here is 2 steps forward, 1 step backwards. So it's the paper from Stephen Bartlett and Andrew Doherty's group in Sydney. So what these people showed is in measurement-based quantum computation, you use a resource state that is from some symmetry-protected phase, a suitable symmetry-protected topological phase, and they showed that you can use it to shuttle information across that spin chain from one end to the other, and that works in the entire phase. You don't have to have a particular ground state, it works in the entire phase. Okay, first step forward above the Miyake paper is, well, this is now measurement-based quantum computation proper, no adiabatic portion. The step backward is, excuse me, the step backward is that this is now about transmission of quantum information only. It's not about processing. Akimasa Miyake's paper was about processing of quantum information. Okay, but what makes this paper so important is the second step forward. And that is, these people here, they imported knowledge from condensed matter physics, something that was already known in condensed matter physics, and that was the classification of one-dimensional SPT phases by group cohomology. So condensed matter physicists knew that already, and these people here imported that into quantum information, and that has stuck. I mean, every subsequent paper, one way or other, goes back to this paper. So this was really a useful insight that the condensed matter physicists had, and that has found its way into quantum computation with the help of these 4. Good. So that's that. Okay. Miyake didn't let it stand there, so he topped it, and he found the first quantum computational phase of matter. So we are now back to computation. We are improving upon shuttling information across, and now talking about quantum computation again. So this is in a chain of in a chain of spins, where a certain symmetry is present, and this S4 symmetry is present. Okay, so one phase is computational. Final result that I want to review here is the image you saw before, the SPT to MBQC meat grinder. So it turns out that Miyake and his collaborator Miller's observation is not special to that particular phase. I mean, it is rather widespread in these one-dimensional spin phases. And what you can do is the following. So you can start with a mathematical characterization of a symmetry-protected phase, which is a symmetry group, and some cohomological information. You crank that through our meat grinder, and out comes a scheme of measurement-based quantum computation. And you know exactly what quantum gates you can simulate and which logical measurements you have. Okay. And so the classification of the symmetry protected phases of matter by this classification scheme translates directly into a classification scheme of measurement-based quantum computation. Yeah, so this is really an endpoint in a certain way. Problem with this result, I mean, if we had this in general, we would be very happy, but the drawback is that it holds only as far as we know in one dimension. So this whole analysis, the classification of MBQC schemes induced by the classification of SPT phases, holds only in one dimension. That's the drawback of this result. So let me tell you what the problem is with one dimension. Yeah, so when you regard measurement-based quantum computation as a simulator of circuits, when you translate from MBQC to the circuit model, you go down to one dimension lower. That is, if you started with a spin chain, when you translate it into a circuit model, you end up in dimension 0. So this means you have a constant number of logical qubits. And of course, constant number of logical qubits is not universal. And therefore, you need spatial dimension 2 or higher for quantum computational universality. So that's a drawback of all this one dimension, all this work in one dimension. Okay, so this leaves us with the question, are there any computationally universal phases of quantum matter in 2 dimensions? And this talk describes one. So now, finally, we get to the subject of this talk. So there is one computationally universal phase of quantum matter, and I should say there have been follow-up works to this work. And yeah, so by now we know a great number of such phases, so it's not only one. But here I talk about the first phase that was discovered, first computationally universal phase that was discovered. Okay, so here is a description of the setting. So what you see here is the lattice and how the symmetries act, because they do not act in a simple fashion. Okay, so let's go through this. So we have a simple square lattice. Locally, that's what it looks like. Globally, we put it on a torus. And the reason for that is that boundary conditions complicate the matter significantly, and so we just avoid that. But torus has no boundaries, and that just kind of makes our life a lot easier. Okay, if you want boundaries, you can have them, but it's extra work, considerable amount of extra work. So much about the lattice, and now the symmetry. So this is how the symmetries act. So here's one. So it has a Pauli spin flip here, Pauli spin flip here, there, and there, and there, and there. They are all acting jointly along this diagonal line. This is one symmetry. Then you have another, which just looks like the former, but it goes, what is that, northwest to southeast. Yeah. Okay, so these are 2 symmetries that you have, and then you have all the translates of these 2, also symmetries, and that is then the generators of your symmetry group. So that's a bunch of Pauli spin flips sigma x acting in this funny pattern. So that is the symmetry that we look at. And for this, not a complete description yet. So the 2D cluster state, if you look at it, it has these symmetries. So there is a phase with this symmetry that has the cluster state in it, and that is the phase that we consider.
Okay, there is a question.
Yeah, what is it?
The question about the initial state of the measurement-based quantum computing model that you get from the meat grinder. How does the group G and cohomological information, omega, inform the initial state of the MBQC scheme? Is it always the same like the cluster state, or do you get different states that depend on the group?
Yes. Yeah. So it's not always the cluster state. The cluster state would be a particular example. So the cluster state would have a specific symmetry group here, and that would be the 4-element symmetry group Z2 cross Z2. And this thing here, what is it at all? It is called a group CoCycle. So that goes a little bit into the representation theory of groups. So without saying too much detail, but what comes into play here is a certain representation, not a linear representation, a so-called projective representation of the group Z2 cross Z2, which is essentially given by the Pauli matrices. There's 4 group elements, 4 Pauli matrices. And yeah, you see the group Z2 cross Z2 is an abelian group. If you look at the Pauli matrices, the 4 elements, I mean the 4 Pauli matrices, they do not commute. So well, you could say they commute up to phase. And what this symbol denotes here, without any technicality, is the quintessential information about these phases that come up when you multiply Pauli matrices. Okay, let me leave it at that. That is precisely what this talks about. So, so we have a symmetry group, projective representations thereof, and then there is some cohomological description of that characterizes the projective representations we have. Yeah, so cluster state would be one example, but you can change the group, and then you can change this topological information, giving you different projective representations, and that gives you different computational schemes. So we saw one example that was different from cluster, and there was Akimasa Miyake's spin 1 chain with a symmetry of the alternating group A4. That was already another example that we saw. So absolutely not. It doesn't have to be the cluster state all the time. It can be very different things. I mean, there's much more phases that we can use here for computations than the one that contains the cluster state.
Thank you.
Yeah, thank you. Thank you very much for that question. And I mean, of course, I have some interest to get to the end of my talk, but much more important for me is that I have an opportunity to answer your questions. So if there's further questions, I'd be very happy to answer them. Until then, let me progress here with my slides. Okay, so I think this is, I went through the setting here. So this is now 2 dimensions, funny symmetry action, cluster state contained in the phase. Yes, indeed, this is the phase that contains the cluster state in one. And I should say, the works that followed up on this work are the same. So it's basically cluster states on different lattices. But in 1 dimension, the earlier work, we have drastically different things than cluster states. But not yet in 2 dimensions. Would be fun to have it in 2 dimensions as well. Okay, so now the result is that in this phase, almost every state, that is all states with the possible exception of a subset of measure 0, are universal resources for measurement-based quantum computation. That is the result. And what I want to do in the remainder of this talk is to tell you a little bit about the techniques that are used to establish this result. There's one technical part in addition, in particular, that I call symmetry Lego. And yeah, I want to talk about symmetry Lego. That's my highlight of the technical discussion. So I hope I can get to it. Overall, the proof uses the framework of tensor networks. So we're representing our ground state in this tensor network fashion. I'm sure many of you are familiar with tensor networks. So these red legs here, they represent the physical degrees of freedom. And then with every site in the lattice, a certain tensor is associated, and the quantum state of this whole net of spins is then obtained by contracting these virtual legs between the tensors. Okay, and yeah, and so we assume translation invariance here, and so every tensor is the same. So the fundamental building block for constructing these states are these tensors, or essentially each one, I mean, either one of those tensors, they are all the same. And now we want to see what we can say about those tensors and how that helps us describe what's going on in this computational phase, or this physical phase that's used for computation. Okay, first comment is, well, we are simulating maybe a quantum circuit, and so where's the quantum register for that circuit? And it lives here on those horizontal virtual legs of the tensor. So this is the location of the quantum register, and as we measure, we move further and further through this network, and the quantum register progresses in this fashion. Okay. So now, a little bit of definition. So very important, and that relates to symmetry Lego that I want to explain later, is this notion of symmetry of those tensors. So they are our basic building blocks, and those tensors have certain symmetries. Yeah, and I mean, we have to establish that. So the first symmetries, I mean, what's going on? We have the physical leg here, and let's say we apply spin flip sigma x to it. We apply all sorts of spin flips to the virtual legs, and that turns out to be a symmetry of the tensor. So when we do that, this gives us back the tensor. And there's other symmetries, as shown here. Whenever we have, so for now, this is only a definition, and why this definition is useful, we see shortly. But if we have those symmetries, we call the resulting state cluster-like. And the motivation for that term is if we add one further symmetry, then we can show the resulting state is actually the cluster state. So this symmetry, or those symmetries up here, this symmetry in addition gives you the cluster state as the only solution. If you don't have the symmetry down here, then there's more freedom, and we call the resulting states cluster-like. Okay? And cluster-like states will be important for what comes up. So here is an overall outline of our construction. So there we were splitting the problem of establishing computational universality into two halves. So the first part is that we show that all states in this 2D phase with the funny symmetries that contains a cluster state, all these states in the 2D cluster phase are cluster-like. That is, their tensors, their tensor network constituents here, they satisfy these symmetries. And part B is that if we have a cluster-like state, that is, the tensors satisfy these symmetries, then we can compute. Okay. All right. So the notion of these symmetries is central for our result. Okay. Let me see how much of this I can show you. Okay. I just want to say the first part of the problem is to get from the physical symmetries that act on our physical spins to the symmetries of this tensor network description of our state. Okay, so there's something to prove that if we have that in the cluster state, this implies the symmetry down here for the local tensors. Yeah, I think, so I do not have too much time left, so I think I'm not going through this argument in detail. Of course, if there's questions, I'd be happy to present details, but let me just give you the gist of it, maybe, and so that I have some time remaining for symmetry Lego, because that's really what I would like to get to. But here is here is the argument overall. And so what we do, so this is our little tensor here with the one physical leg and the virtual legs. And we can write it, we know that we can write it as the perfect tensor, which would be for the cluster state. And that's shown in blue here. And then this brown piece, which we call a junk tensor. So everything that's kind of messing up the cluster properties is contained in this junk tensor, but hopefully not so much. And here is the crucial property of the junk tensor. So we can show, and there's considerable work going into showing this property, is that this junk tensor commutes with the Pauli spin flip operator on the physical leg. Yeah, so the spin flip operator moves right through the tensor without showing it, and that works anywhere in the 2D cluster phase. So that is what there is to show, and that is a little bit of a long winding argument. But once you have that, so we know that we have the desired cluster-like symmetries already for the cluster state, and then by this property we can show that that the same holds also for the state anywhere in the cluster phase by the two facts that it holds for the cluster state, and we have this propagation relation for the junk tensor. Okay, that is the core of the argument. It requires that this property holds, and this argument stretches across a number of slides. I think I just skip it, but I mean later, I mean if there's questions about it, I'd be happy to go through it. Okay, but this is kind of, you see maybe 3 or 4 slides. This is the argument, but the result is what I just said. Anywhere in the cluster phase, we have the cluster-like symmetries. But the cluster symmetry, yeah, the cluster symmetry, let's go back. The cluster symmetry has a Pauli operator sigma z acting on the physical leg, and the sigma z does not propagate through the tensor. And so we are losing this final symmetry that separates cluster-like from cluster, as we would expect. I mean, we go through the phase and expect something to change. Okay, so that is the result. In the entire cluster phase, we have those symmetries of the tensor. And now we take those symmetries and play Lego with them for the purpose of computation. Okay, so let's do at least a little bit of this. So this is the clock cycle. This is the simplest thing, again, that you would want to do on your lattice, and that is to establish computational wire. I mean, sure, before you can do any gate, you want to be able to do the identity operation. And that is now a rather complicated song and dance. So you need several kind of columns, I mean, yes, several layers of your resource state to implement the identity. Yeah, and it gets wider and wider the larger the circumference of your torus is. Okay, and so, but this is the symmetry Lego. This is really the interesting part that I wanted to show. So we have an incoming Pauli operator here on the virtual leg, and now using the symmetries that we have, it splits into all sorts of weird stuff, getting very, very complicated, stretching across the circumference of the lattice, but thereafter shrinking and coming out after a while as what it entered. So in those symmetries, we have those physical legs, the Pauli operator sigma x acting on them, but when we implement the wire, we measure those physical legs in the sigma x eigenbases, and so essentially those links are being contracted. And so what we have in yes.
Can you just explain just for me one more time what the virtual leg means versus the physical leg?
Yeah, virtual leg versus physical leg. Yeah, sounds like a significant difference. Yeah, so maybe let me go back to this picture. Yeah, so this is, I don't know, This will be easy to understand for anyone who has ever worked with matrix product states. So matrix product states are this, but in one dimension. Yeah, and so the idea is about matrix product states is to describe short-range entangled states. So so something, I mean, not local, but sort of close to local. And so in the 1D case, what I call a tensor here is just a matrix. Well, sorry, matrix with a label. And so the physical, yeah, to address your question, the physical leg is corresponding to an actual particle. Yeah, it is, I mean, you have a state of actual physical particles, actual degrees of freedom, and each leg represents a particle. Yeah, and the tensors, they just organize the information that we know about these states. So, well, there is a bunch of information contained here, and we contract those tensors along those legs here. So that is, I mean, these are indices like matrix indices or tensor indices, and they are contracted over, and they are contracted, and so those tensor legs is what we remain with after the contraction, and that gives us a quantum state. If I had a pen here, I could write a formula. Unfortunately, I don't want to. Oh, let me see. Do I have a pen here? Let me see. Redact. Oops. Oh no, please not.
That's all right. I want you to be able to continue, but this helps. Thanks.
Okay, it does help. So I, you know, maybe you yourself and many here in the audience, they will have heard of matrix product states. So I'm using the same concept, but a dimension higher up. So when we go from matrix product states to higher dimension, we get into this terrain of tensor networks. Good. Okay, thank you very much. So let me see, where was I? Somewhere, yeah. Okay, so basically all that is left for me to do is to advertise Symmetry Lego. So this is this is kind of the simplest thing you do. I mean, the simplest quantum operation is you want to do the identity operation. And kind of the high level comment of this picture is that the tensor symmetries, they ensure they ensure that you have the identity that you can perform. And it is exactly like in the one-dimensional case, it is a consequence of the tensor symmetry. Okay, maybe that's kind of the first thing to say, and I hope kind of when you see this picture, I hope it makes you curious. And if it makes you curious, you can always have a look at the paper and then maybe get a deeper technical understanding of what's going on here. But of course, we don't only want to talk about transmitting information. We want to talk about computation, and that's really the final bit of the construction. So to compute, we move away with our measurement bases. So remember, the algorithm is implemented with a choice of measurement bases. So far, for wire, we use the symmetry respecting X basis, and now we are moving away from the symmetry respecting X basis. And we do this for the cluster state first, and then talk about the phase later. So when you do this in certain locations, again, the symmetries tell you that you can do certain gates, and they are shown here. So you can do this exponential of sigma x. So that's a local x rotation. You can do the same if you change the measurement angle in some other place. You can do the same, but this time you get a rotation about the z-axis, and you do it in yet another place, namely here, and then you get an entangling gate. So this is what you can do, and it turns out, I mean, you have all these gates here, and whatever else, and then all the translates, and that is a universal set of gates. turns out. Okay, so this is how you get the gates at the cluster point. And now you want to do the same in the entire phase. And I'm shuffling a lot of calculation under the rug. But what comes out is, in the cluster phase, it essentially works the same. It is just given a fixed measurement basis, your rotation angles become smaller. So they are multiplied by this number that is in magnitude smaller than 1. Okay, so that I'm just saying it, there is a proof behind it, but it is long. Okay, and that completes the construction. So you have the same universal set of gates in the entire phase. So that brings me to the end of my talk. So just let me restate the result. We have this funny phase in 2 dimensions with this symmetry action that contains a cluster state, but any state in that phase can be used for universal quantum computation. The computational power is uniform across the phase. I think I have 2 more slides. So what did we learn? First thing, the phenomenology of computational phase of quantum matter extends all the way to universality. So the field for a long time talked about what can be done in spin chains and establish the relation of, the notion of computational phase of matter there. But 1D can never give you universality. And so you can at least find one, and by now we know a few more, you can find a few phases of quantum matter in 2 dimensions that are indeed universal, computational universal. Okay, so that's kind of the message of this talk. And also, the gate operation, quantum gates follow from the symmetry properties. So that is the symmetry Lego part of it. Good. Yeah, so in outline, I think I said it. So we have one 2-dimensional phase with uniform universal computational power. And an open question is, well, now we have one phase and indeed a few more. What about classification? In spatial dimension 1, we had a classification. Can we get the same in dimension 2? Okay, and just kind of an advertisement here. So try some symmetry Lego if you like it. If you want to inform yourself about this work, here's a couple of references. So what I talked about today is in here. And then there is related work, follow-up work, and I give you two references here. One from our group and one from the VIAFI group. Thank you.
Okay, thank you for that wonderful introduction to this area. We don't have any more questions in the Q&A right now, so I want to encourage audience members. We have a few minutes left on the hour to submit questions while we have Robert here. And maybe I can ask some more open-ended questions while we're seeing if questions come in. Mm-hmm. So one, as an experimentalist, they may be somewhat naive. You know, I really liked your initial papers when I could find a mapping from qubit systems and how to create a certain cluster state, and I know how to do the measurements, etc. For these new phases, I guess, what is the prospect of using them for computation, or is there any advantage over the one measurement-based scheme that was the initial measurement scheme?
Mm-hmm. Yeah, I think this needs to be judged case by case. So there is always disadvantage and always advantage, and then whether that's a net gain or loss, I mean, needs to be discussed on a case by case basis. So let me get into this a little bit. So what's the gain? So maybe, I mean, you do not. So maybe in the system of your choice, maybe it's optical lattices, or I don't know. You do not need to hit the cluster state perfectly. So you can get to something nearby, and it will still be good for computation. So that's the advantage. Yeah. So it gives you more flexibility. You can have, so I mean, you don't need one specific state. So just if you have a computational resource state, usually there's a lot of states nearby that are also good for computation. So that's the advantage. But there is a flip side, and that is, I said those states have the same computational power. This is kind of the computer science perspective. There is fine print, and this fine print is, well, there is overhead, but it is a constant multiplicative factor overhead. So for the theorist, that is like nothing, but for the experimentalist, it might actually be not so good. So we know, I mean, I didn't talk about decoherence, dephasing, and so on and so forth, but that would need to be taken into account. And so if the computation blows up just by a little bit, maybe a factor of 3, which is not very much in those constructions, then this means that, I mean, you're more susceptible to all the other problems that you may have with your real device. And so that's a disadvantage. Yeah, so, I mean, from the computer science perspective, it's just the same. You have a factor 3, factor 10 overhead. The computer scientists don't care. I think the experimental physicist does care. And so it is a trade-off.
But I'll just be advocate. But don't you always, it has to be a pure state, right? You never take into account that you have these like mixed states.
Well.
And do you also have to always know the state in order for it to be useful?
Okay, so let me begin with the second part of your question. And that is kind of already Miyake's point. You don't need to know the state. But you need a little bit of information about it. So I mean, that was Miyake's partially adiabatic scheme. So let me give you the answer for our scheme, and it is in here. So you need to know that number nu. So I mean, you are somewhere in the phase, and well, you just need one complex number. I mean, every point in the phase is described by a complex number whose magnitude is 1 or less. And you need to know what that number is, yeah, in order to run the scheme. Because you know, you're thinking you're implementing a rotation with a certain rotation angle, but then really you implement a rotation with a smaller angle. So you need to know what that number is. And I mean, you can measure, you can use part of a resource state to measure what that number is, but that's something you need to know. It's a tiny bit of information that you need to know about the state that you're dealing with. Yeah, so that so much about the second part of your question. And now your question had a first part, and what was that again?
The first part was a comment on the purity of
purity. Yes, purity. Exactly, the purity. So so the work that is published requires pure states, but yeah, I mean, we'll continue to work on this, and we think the purity, well, with fine print, purity will not be required. So yeah, so what is in the literature requires purity, but purity is probably not required. So what you really need is that I mean, this is SPT, so you have some, I mean, in 1D, you would have a string order parameter, and yeah, and here you have in 2D, you have something slightly different. You have some sort of fractal order parameter or something along those lines. So what you really need, it seems, is non-vanishing order parameters, symmetry, short range, entangled. So this is what you need. Purity is probably not required. But wait, check the archive. I mean, we are working on it. I mean, this is
that of course is music to my ears. Cool. We'll check.
Yeah, but symmetry, yes, but I mean, you can be mixed, but symmetry is required as far as we know.
Okay, great. So we have a few more questions from the audience. I would actually like to ask all three if you have a few more minutes before we close the session, or are you limited in time?
I'm not, no.
Okay, so why don't we go ahead and ask the three, and then we'll close the session. Can you elaborate more on the overhead? Is it similar to the overhead that arises in the circuit model case when switching from Clifford plus T to Clifford plus square root of T, or is it of another nature?
Let me think. Yes, I would say it is of a different nature, but let me see. Is there a connection I could see? Yeah, no, I think it is different. So let me talk about. I mean, at least who knows? Maybe someone can see a connection. But let me focus on the differences here. So when you move away from the ideal situation, that is your cluster point. So what then happens is, I mean, you get difficulties, and I've kind of shuffled this under the rug. I mean, yeah. So the difficulty is that when you in the phase, when you measure in away from the symmetry respecting basis, remember the symmetry respecting basis gives you wire, so this is relatively uninteresting. So if you want to do anything more than wire, you need to move away from the symmetry respecting basis, but then you get another thing that you don't want, and that is logical decoherence. Then that can be explained in terms of those junk tensors that I mentioned earlier. So what's happening, where do I have my junk tensors? Yeah, the junk tensor. So we have the cluster, so the real tensor is the cluster tensor modified by those junk tensors. And so what's happening is that your logical system, which lives down here, becomes entangled with your junk subsystem when you measure away from the symmetry respecting basis. And so effectively, that leads to logical decoherence. And that needs to be very carefully managed. And the way you do manage that is you measure away from the symmetry respecting basis, but only a tiny little bit. So this is like driving on an icy road very, very slowly. And so because you are limited to measurement bases very closely to the symmetry respecting basis, and then you have this factor nu that also comes in, because of that, you incur the overhead. So it is really, yeah, you need to accumulate rotation angles in tiny, tiny steps. So that is the real, as opposed in the cluster case where you're not limited in such a way. So this is where the overhead comes from. So it's a little bit different from changing from one set of magic states to another set of magic states.
Okay, thank you. And maybe one final question. Can you comment on the classical information that needs to flow through the computation?
Yes, that is completely unchanged from the cluster case. Yeah, so we know what's happening in the cluster case is that the measurement the measurement outcomes that you get somewhere, they influence the measurement basis elsewhere. So they lead to a potential flip of the measurement basis between two positions, and that is completely unchanged. It's exactly the same as in the cluster case. Yeah, so same classical side processing as for the cluster case.
Okay, with that, because we're a few minutes over, I think it makes sense. I want to thank you again on behalf of the audience members and the NQN for coming and sharing this work with us. And this, I guess, ends the seminar. Thank you so much.
Yeah, my pleasure. Thank you for having me.